Okay, so learning target number 4 is about gravity. So we're going to analyze gravitational systems and use the correct gravity equation. Okay, so let's get a brief idea of what we're talking about here. Okay, so first, people experienced gravity, right? Like if we have an object and we let go, it falls, and we say, okay, I experience that, I see that, I'm going to call that gravity. Then Newton came along, and you know the whole story about like the apple falling and all of that. Well, he had this really famous thought experiment, and he said, what if I took a cannon and I placed it on top of a really, really, really tall mountain, okay? And it's a super powerful cannon, and I shoot off the cannonball, and it's going to make a parabolic motion, right? It's pointed perfectly horizontal, so it will fall to the earth. Now, what if I increase my amount of gunpowder, and so it's going to go a little bit further, and then it's going to go a little bit further? Well, it turns out, and what he was thinking is, what if the way that the cannonball is shot and it's falling, what if that curvature of which it's falling matched the curvature of the earth? What if we shot the cannon and the earth was essentially falling out from underneath the cannonball? It was falling at this same rate, and eventually it would come around and it would hit the back of the cannon. It wouldn't get any closer or further away, and that's what we call an orbit. And that's how orbits work. The moon is actually falling towards the earth. It's just falling at this same rate that we're moving out from underneath it. Okay. So that was a big thing back then, this idea that anything with mass has gravity. And even though the moon seems to be floating up in the sky, gravity is acting there as well. Okay? Now, remember, we called gravity a field force, not a contact force. We don't have to actually be in contact with an object for the force of gravity to be applied, just like the pen. The pen is not physically touching the earth, but it is pulled down to the earth. Okay. Now, we have an equation that describes what's happening here. And that equation is the force due to gravity is equal to G, which is this gravitational constant, multiplied by mass 1, mass 2, over the distance between the masses, or the distance between the center of mass of the masses squared. Okay. Now this constant G, and all constants, they just help to find that ratio between two values, to find how two values relate to one another. Okay, and so this constant is 6.67 times 10 to the negative 11th, and we have units of Newton meter squared per kilogram squared. Now, really interesting equation. We have components that are proportional to the force due to gravity, and we have components that are inversely proportional. Okay? And here's what we mean. Add this over to this, actually, you know what, let's do it right underneath here. Directly proportional means that if one value increases, then the other value increases. Okay? Or if one value decreases, the other value decreases. Then those two values or components are proportional or directly proportional to one another. Inversely proportional is the opposite of that, that when one of them increases, the other one decreases. Or vice versa, if one decreases, the other one increases. Okay? Now, when you look at this equation, we're going to relate all these components back to force. G is a constant. That's not going to change. But the mass could change, or the distance between the center of mass of the two objects could change. How are the masses related to the force? And how is that distance related to that force of gravity between them? I like to look at this and we kind of think of it as a fraction. If I increase what's on the top of the fraction, then the overall becomes bigger. Okay? When that got bigger, this got bigger, so that'd be directly proportional. Or if I decrease my mass, then overall this gets smaller, so that gets smaller. And so both of them went down, so that's directly proportional. Now, what if we're on the bottom of our fraction? Like if we have 1 over 5, and then we change that to 1 over 10. I increased the bottom of my fraction there, and it made the overall smaller. So when this got bigger, that got smaller. Okay? And that's called inversely proportional. And then we have the square on there. It's not just inversely proportional, it has an inverse square component to it. And I think that's best seen down here. But what we're saying, if the distance of an object from another is doubled, okay, so this gets twice as big as it was before, then the force of attraction would also be reduced by 2 squared, because it's not just r, it's r squared, or 4 times weaker. It'd be a fourth of what the force would be, as a fourth of what it was before. Okay, now here is one way that I like to approach these kinds of problems. Okay, here's how I like to approach these kinds of problems. I like to plug in convenient numbers and then increase and decrease those numbers and look at the result. If I'm not seeing right away what's happening with an equation, there's nothing stopping you from putting in numbers and then observing what happens when you change those numbers. Okay? So what if, for this hypothetical situation here, I'm going to make mass 1 and mass 2 and r, they're all going to be 5. Okay, so I have this equation, and I'm going to have mass 1 multiplied by mass 2 divided by 5 squared. Again, I just chose 5. You could choose any number, and they don't all have to be the same either. Okay, so that gives me a force of 1. Okay. Now, here it's saying, what if m1 was twice as much as it was before? So it's 2m1. So instead of being 5, now we have 10. When mass 1 doubled, my force doubled. Okay, so what's the result of this? Well, we got twice as much force. Okay, all right, what if instead of doubling, mass 1 tripled? So we'd have 15 instead. Then the force also triples. When one got bigger, the other one got bigger, and they're directly proportional to one another. Okay, make a prediction now. What if it's 2m1 and 3m2? Okay, what do you think? Write it down, and then let's check. Okay, so have you made your prediction? So we're going to go twice m1, so that'll be 10, and then 3 times m2, so that'll be 15, and we end up with 6. 2 multiplied by 3, so we have 6 times the force that it was before. What if one of the masses is half as much as it used to be? So we have 2.5 instead of 5. It's half as much. Everything else stayed the same. Now instead of 1, we have 0.5. So the force was half as much as it used to be. When one got bigger, the other one got bigger. When one got smaller, the other one got smaller. That is directly proportional. This sign here means relationship. So the force has a directly proportional relationship to the masses. Okay? Now let's make some changes for that distance between the objects. So we'll go back to our base again. 5 multiplied by 5 divided by 5 squared, right? And the force is 1. Now let's change this distance component is going to be twice as much. Okay. Remember, we have the squared factor. And so it's going to be a fourth. Not a half, but a fourth of what it used to be before. So we have 1/4 the force that it was before. When we double the distance between the objects, the force is a fourth of what it used to be. Because our relationship is inverse. When one gets big, the other one gets small, but it's also squared. Okay? So what do you think for triple the distance? What do you think would happen to the force? Okay. Now I'm a ninth of what I was before. So that would be a ninth. Why wasn't it a sixth of what it was before? Well, if the component that's changing, it's 3r, but then you take the square of that. 3 squared gives us the 9, so it's a ninth of what it used to be. Okay, now, but what if it was a 1/2? Oh, that's interesting. I want you to make a prediction on that before we plug it in. What do you think? The 1/2, but then we have the squared component. Okay? So instead of 5, with this example that I've been working with, I'm going to pick 2.5. It is 4 times as great as what it started with. When one got smaller, the other one got bigger, squared. And a third. Now I'm not going to plug that one in. We can make this prediction, right? Because we saw here we went from 2, we got a fourth, and when we got 3, we got a ninth. Because 2 squared equals 4, 3 squared equals 9. Well, 2 squared equals 4, so 3 squared would need to be 9 times the amount of force. Okay. Now we can use this amazing equation and what we already know about the force due to gravity, and we can actually calculate the mass of the Earth. Remember that base equation that force due to gravity is the value g, m1, m2 over r squared. Okay. What if m1 is just the mass of an object and m2 is the mass of the Earth? And we know that force due to gravity, just in general for Earth, is mass of the object, which we're calling m1, times it by g, or that acceleration due to gravity, that 9.81. How can we combine those and calculate for mass of the Earth? Okay, I want you to give that a go, and then select the next video, and we will talk through that.